Dear student, welcome in the class of mathematics. Today we have to see linear differential equations. So what is linear differential equation? The differential equation of the type dy by dx plus py equal to q, where p and q are functions of x, is called as linear differential equation. Now you have to find the solution of linear differential equation. So consider this linear differential equation dy by dx plus py equal to q, where p and q are functions of x. This is equation number 1. Transfer this py to this side, and so we get dy by dx is equal to q minus py. Now multiplying by dx on both sides, we get dy is equal to q minus py into dx, that is q minus py dx minus dy equal to 0. This differential equation is of the type m dx plus n dy equal to 0. So comparing, we get m is equal to q minus py and n is equal to minus 1. Now here we have to find derivative of m with respect to y and derivative of n with respect to x. So taking partial derivative on both sides with respect to y, we get dy by m by dy by y is equal to dy by y of q minus py, and taking here partial derivative with respect to x, we get dy by n by dy by x is equal to dy by x of minus 1. Taking this dy by y inside 1, so we get dy by m by dy by y is equal to dy by q by dy by y minus dy by y of py, and as minus 1 is constant, derivative of minus 1 with respect to x is 0, so we get dy by n by dy by x is 0. Now here we know p and q are functions of x, they both doesn't contain y, and so derivative of q with respect to y is 0, and here we can take p outside, and so we get dy by m by dy by y is equal to 0 minus p dy by y by dy by y, and dy by n by dy by x is equal to 0. Dy by y by dy by y is 1, so we get dy by m by dy by y is equal to minus of p into 1, that is minus of p, and dy by n by dy by x is equal to 0. Here we get dy by m by dy by y not equal to dy by n by dy by x, and therefore this differential equation 1 is not exact. As this equation 1 is not exact, we can make it exact by multiplying integrating factor. So first we have to find the integrating factor. Here consider 1 upon n dy by m by dy by y minus dy by n by dy by x. Value of n, which is minus 1, so here we get 1 upon minus 1, that is minus 1. Value of dy by m by dy by y, which is minus p, and dy by n by dy by x, which is 0, and so whole this value is equal to minus 1 into the bracket minus p minus 0, so which is minus 1 into minus p, so which is p. And therefore here we find the value of 1 upon n dy by m by dy by y minus dy by n by dy by x, which is p, and you know p is a function of x, so this is function of x alone, say it is fx. Therefore 1 upon n dy by m by dy by y minus dy by n by dy by x is equal to p, means fx, that is p, and so we get integrating factor is equal to e raised to integration fx dx. Putting the value of fx, we get e raised to integration p dx. So this is the integrating factor. Now multiplying this integrating factor with the differential equation 1, we get e raised to integration p dx into the bracket q minus py dx minus e raised to integration p dx dy is equal to 0. This differential equation 2 is obtained by multiplying integrating factor, so this differential equation 2 should be exact. This differential equation is of the type m dx plus n dy is equal to 0. So value of m is e raised to integration p dx into the bracket q minus py, and value of n is minus of e raised to integration p dx. As this differential equation 2 is exact, its solution is given by the formula integration m dx keeping y as a constant, and integration terms in n not containing x and dy equal to c. Now put the values of m and n here, and so we get integration e raised to integration p dx into q minus py dx keeping y as a constant plus integration. Now here we have to write the terms in n not containing x. There is only one term in x which contain x, and so there is no term not containing x in n. So here we get 0 and equal to c, and therefore integration e raised to integration p dx into q dx keeping y as a constant, minus integration e raised to integration p dx py dx equal to c. Integration of 0 is 0. So here we separate this integration. And therefore, as here p and q are functions of x, and so they doesn't contain y, so there is no need to write y as a constant in the first integral. And in second integral, as y is a constant, we can take outside of that integral. And therefore, here we get integration e raised to integration p dx into q dx minus y integration e raised to integration p dx into p dx is equal to c. And therefore transfer this negative sign to that side, and so we get y e raised to integration p dx into p dx is equal to integration e raised to integration p dx into q dx plus c. This is equation number 3. Now here we have to evaluate this integration e raised to integration p dx into p dx. So say this is I. Put here integration p dx is equal to t. So differentiating with respect to x on both sides, we get p is equal to dt by dx. Here integration and derivative get cancelled. Now put this value of p here, so we get I is equal to integration e raised to, this is t, value of p which is dt by dx into dx get cancelled, so we get I is equal to integration e raised to t dt. Integration of e raised to t with respect to t is e raised to t, so I is equal to e raised to t. Now put the value of t as integration p dx, so we get I is equal to e raised to integration p dx. Now put this value of I in equation number 3, so we get y e raised to integration p dx is equal to integration e raised to integration p dx into q dx plus c. We can write this integration as q into e raised to integration p dx, and so we get y e raised to integration p dx is equal to integration q e raised to integration p dx plus c. This formula gives the general solution of linear differential equation 1. Now we have to see some examples on linear differential equation. So see the first example. Solve dy by dx plus 4x upon x square plus 1 into y is equal to 1 upon x square plus 1 bracket cube. Solution. Now see this differential equation. This is of the type dy by dx plus py equal to q, where p and q both are functions of x. So this is the linear differential equation. So here value of p is 4x upon x square plus 1 and value of q is 1 upon x square plus 1 bracket cube. This is differential equation number 1. Now here integration p dx is equal to integration 4x upon x square plus 1 dx. We can write this 4x as 2 into 2x, and so we get this is equal to 2 outside, integration 2x upon x square plus 1 dx. Derivative of x square plus 1 is 2x, and so we can use the formula integration f dash x upon fx dx, and value of this integration is equal to log of fx, and therefore integration p dx is equal to this 2 as it is, and this integration derivative upon a function, so it is log of this x square plus 1. Now solution of linear differential equation. As this differential equation is linear, its solution is given by y e raised to integration p dx is equal to integration q into e raised to integration p dx plus c. Now put the value of integration p dx here, so we get y e raised to 2 log of x square plus 1 is equal to integration value of q, which is 1 upon x square plus 1 bracket cube, into e raised to integration p dx means e raised to 2 log of x square plus 1 dx plus c. Now transfer these 2 to the power of x square plus 1, so we get y, e and log get cancelled, x square plus 1 bracket square is equal to integration 1 upon x square plus 1 bracket cube. This value is x square plus 1 bracket square dx plus c. Here x square plus 1 bracket square get cancelled, and so we get y into the bracket x square plus 1 bracket square equal to 1 upon x square plus 1 dx plus c. Now use the formula here, integration 1 upon x square plus h square with respect to x. So we get y into x square plus 1 bracket square equal to tan inverse x plus c. So this is the relation between x, y and constant. So this is the general solution of the given linear differential equation 1. Now consider the second example. Solve dy by dx plus 2y equal 2y tan x equal to sin x. Given that y equal to 0 when x is pi by 3. Here he has given some extra condition, means here we have to find the particular solution. So first we have to find general solution, and then we have to put the value of particular value of c, so we get the particular solution. So first find out the general solution of this differential equation. So give this differential equation number 1. Now we observe that this is the differential equation of the type dy by dx plus py is equal to q, means this is the linear differential equation. So value of p is equal to 2 tan x and value of q is equal to sin x. Therefore, integration p dx is equal to integration 2 tan x dx. Take out 2 as a common. So we get integration p dx equal to 2 integration tan x. Tan x means sin x upon cos x. So we can write this is minus 2 minus of sin x upon cos x dx. Again use the formula integration f dash x upon fx, and which is log of fx. And so here we get integration p dx is equal to minus 2 log of cos x. Now, as this differential equation 2 is linear, its solution is given by the formula y e raised to integration p dx is equal to integration q into e raised to integration p dx plus c. Now put the value of integration p dx, which is minus 2 log of cos x. So you get y e raised to minus 2 log of cos x is equal to integration value of q, which is sin x, e raised to integration p dx means minus 2 log of cos x dx plus c. Now transfer this minus 2 to the power of cos x, and e and log get cancelled. So we get y cos of x raised to minus 2 equal to integration sin x cos of x raised to minus 2 dx plus c. Transfer this cos of x raised to minus 2 to the denominator. So this will become y upon cos square x is equal to integration sin x upon cos square x dx plus c. We can write this value as y cos square x equal to integration sin x upon cos x 1 upon cos x dx plus c. Sin x upon cos x is a tan x, and 1 upon cos x is a sec x, and so we get y upon cos square x is equal to integration sec x into tan x dx plus c. And you know sec x into tan x dx, integration sec x into tan x dx is a sec x, and so we get y upon cos square x is equal to sec x plus c. Now multiplying by cos square x, 1 upon cos square x is sec square x, so we get y sec square x is equal to sec x plus c. Now this is the general solution of the given differential equation 1. This is equation number 2 now. Now he has given that y is 0 when x is pi by 2. So put y 0 and x equal to pi by 3 in this equation 2. We get 0 is equal to sec pi by 3 plus c. Value of sec pi by 3 is 2, so we get 0 is equal to 2 plus c, so c is equal to minus 2. Now put this value of c equal to minus 2 in equation number 2, we get y sec square x is equal to sec x minus 2. And we put here particular value of c, so this is the particular solution of the given differential equation 1. So in next lecture, we will see some more examples. Thank you.